So for those of you that didn't watch the kind of review lecture, the point at which we are at is we say the presynaptic neuron, or neuron number 1, has fired at a high enough frequency, we'll say 100 times per second, to release enough neurotransmitter onto the postsynaptic neuron, neuron number 2, to open up enough ligand-gated channels, or frequency at which the ligand-gated channels open up, some combination of those two things, to allow enough sodium in to neuron number 2, into the dendrites of neuron number 2, so that enough sodium actually gets into the Hillock region to cause the Hillock region to depolarize, to become more positive, so that it actually gets from -70 to -55 millivolts. Okay. So simpler way of saying this, the presynaptic neuron has fired at a high enough frequency to actually depolarize the Hillock region of the postsynaptic neuron to threshold. And now we want to take a look at what's going to happen. The beginning, the first part of this is going to be a review of the action potential, and the repolarization and refractory portion is going to have a lot of very new content to it. Okay, that's going to be important for the rest of the semester. So just to create a visual, all these waves of positivity, depolarizations, whatever you want to call them, are headed from the different dendrites towards the hillock. Okay. Sodium is coming in, right, through all of these ligand-gated channels, because the neurotransmitters are causing them to open up and allowing sodium to rush in, making these regions more positive, and these positive waves are all headed towards the hillock. And that's happening not in just one location, but from all of these different locations in different dendrites that the presynaptic neuron here synapses with. So these waves of positivity, these depolarizations are all headed towards the hillock of the postsynaptic neuron, neuron number 2 here. And again, the presynaptic neuron is firing at a high enough frequency to actually allow enough sodium in so that within the hillock we have depolarized to -55 millivolts from -70. What we would say is that the postsynaptic neuron, neuron number 2, has now hit threshold, and it is going to generate an action potential. So let's go ahead and take a look specifically at the hillock. We're going to blow the hillock up, just like we've blown a synapse up, and discuss what's happening in there. The beginning part of this, those of you that have taken a course with me have seen this before. Okay, this is the hillock, right? Here is the kind of the cell body, all right? So in the hillock, we're at -70 millivolts, okay? And as well as down the whole length of the axon, for that matter, and in the cell body. But all of those waves of positivity, those depolarizations, are heading from the dendrites towards the hillock region, right? Making all these other regions more positive as the sodium ions flow into these regions. You know, so let's just make something up. We'll say that the cell body has gotten enough sodium within it so that it has risen to -50 millivolts. Okay, this portion of the cell body. Okay, as the sodium ions move in to the hillock, right, some of that positivity is going to dissipate for the reasons that we discussed. But enough sodium ions have gotten actually into the hillock to raise the hillock's membrane potential from -70 to -55 millivolts. Okay, so we have hit threshold. What exactly does this imply? Well, in the hillock, what we have are what are called voltage-gated sodium channels. Voltage-gated sodium channels. Okay. These are not non-specific cation channels. These are actually specific cation channels. They're specific to sodium ions, and they're voltage gated. Okay? They're not ligand gated, they're voltage gated. That implies if the voltage within a particular region changes enough, these channels will open. In particular, the vast majority of these voltage-gated sodium channels will open if the voltage increases by about 15 millivolts. If the membrane potential goes from -70 and becomes 15 millivolts more positive, that's a voltage change, and these voltage-gated sodium channels in the axon hillock will actually open. Well, as I've discussed with you, enough sodium ions have actually come from the dendrites into the cell body, into the hillock, to make the hillock 15 millivolts more positive. And if we make the hillock 15 millivolts more positive, then, as you guessed, probably, these voltage-gated sodium channels are all going to open up. And what does that mean within the hillock region? The hillock region is going to become much more permeable to sodium ions. What do we know about sodium? Sodium's high in the interstitial fluid. It is low in the intracellular fluid, so it has a chemical driving force to come in, and it also has a strong electrical driving force to come in. Okay, so if you open up a whole bunch of voltage-gated sodium channels, you can imagine what's going to happen here. Sodium ions are going to rush in through these voltage-gated sodium channels that just opened up because of the change in the voltage, and the inside of the hillock is going to become very positive. Enough sodium ions are actually going to rush in. It's actually not a huge number, but enough come in to make the membrane potential in the hillock rise to about positive 30 millivolts. We'll talk about why we get stuck at positive 30 millivolts in a second, but what I want to actually show you is where this big wave of positivity is going to move. Okay, so we hit threshold inside of the hillock, which means that we rise by 15 millivolts, become 15 millivolts more positive in the hillock. We call that threshold because if we get to that value, then all the voltage-gated sodium channels in the hillock will open. At that point, sodium will rush in. Enough sodium will come in to actually drive the interior of the hillock up to positive 30 millivolts. And where do you think all of this sodium is going to move? Well, the membrane potential down the axon hasn't changed. We've made the hillock region rise to positive 30 millivolts due to this large influx of sodium ions through the voltage-gated sodium channels, but down the length of the axon, right, it's still all -70. This is, again, why understanding that when we talk about the membrane potential becoming more positive, it's only happening in isolated regions. This is not happening throughout the entire neuron. This is only in the hillock right now. So what we want to think about is where are all of these positively charged sodium ions going to move to next? And the obvious answer is they're going to move towards a subsequent region of negativity. Regions of positivity are always moved towards regions of negativity. Well, the hillock is now positive 30 millivolts due to this large influx of sodium ions, and these sodium ions are now going to move into the next region of the axon, which is still at -70. Let me show you. All right, so again, we say this is the hillock region right here. Then we have the rest of the axon too. Okay? Voltage-gated sodium channels just opened up in the hillock because we got to threshold, and a whole bunch of sodium came in through those voltage-gated sodium channels. Sodium has a chemical and electrical driving force to enter and made the interior hit positive 30 millivolts. Okay, this region is still -70. So all these sodium ions are going to move into the next region. Well, I can go ahead and tell you what lines the entire length of the axon are voltage-gated sodium channels. Okay, just like in the hillock region, voltage-gated sodium channels line the entire length of the axon. So as these sodium ions from the hillock region move into the subsequently negative region of the axon, where it's still -70, it's going to make this region more positive. And you only have to raise the membrane potential within that region 15 millivolts to get more voltage-gated sodium channels within the next region to open up. Very easily accomplished. Okay? So voltage-gated sodium channels in the next region are now going to open because we made the membrane potential rise much more than 15 millivolts. So now a whole bunch of voltage-gated sodium channels are going to open. Sodium is going to rush into this region, and it's going to make this region positive 30 millivolts. Okay. Where is or are all of these sodium ions going to move to next? Well, think about it. The next region, down the subsequent region, down the length of distally down the axon is still -70. So the sodium ions are going to get pulled into the next region, make that region more positive. And now all the voltage-gated sodium channels, the membrane of that region, are going to open up. Sodium is going to rush in. It's going to make this region +30. And then where the sodium ion is going to go, they're going to move into the next region. Right? And they're going to make the next region positive enough so that the voltage-gated sodium channels open up. Sodium's going to rush in, make this region +30, then they're going to move into the next region. Okay, what you're seeing here is what's called propagation of the action potential. The action potential, which is a non-decremental wave of positivity, is propagating down the length of the axon. So let's just quickly define what an action potential is. I did it already, but I want to make a little bit more sense out of it. Okay, so when you get the Hillock region to threshold from -70 to -55 millivolts, because enough sodium ions actually get into the Hillock region, that's when an action potential is going to occur. It occurs because all the voltage-gated sodium channels in the Hillock are actually going to open. Okay, so that's why an action potential occurs, is because the Hillock region hits threshold. But what is an action potential? An action potential, by definition, is this, again, non-decremental electrical wave that travels down the length of the axon into the axon terminals and into the buttons. So what makes it decremental? First of all, non-decremental, excuse me. What makes an action potential non-decremental? Because that's really its definition. First of all, realize what decremental is. Okay? A decremental electrical wave is like what's coming from the dendrites. As the electrical impulse moves away from the site of origin, it dissipates or it decrements, right? It falls apart. I'm intentionally not getting back into all of the detailed definitions of these because we already did them in other courses, but when a wave of electricity is decremental, it's called a graded potential, not an action potential. What you're seeing coming from the dendrite regions are what are called graded potentials. They actually decrement as they move away from the site of origin for the reasons that we discussed earlier. Now, action potentials don't decrement, right? It's +30, +30, +30, right down the entire length of the axon. It never changes. It's +30 throughout the entire length of the axon. The signal doesn't decrement. And the reason the signal doesn't decrement is because voltage-gated sodium channels exist throughout the entire length of the axon. So the sodium ions come into one region, they go into the next region, they open up more voltage-gated sodium channels, sodium rushes in, makes that region +30. So because of the fact that the entire axon and axon terminals and buttons are lined with, you'll see the buttons in a second, but are lined with voltage-gated sodium channels, the signal doesn't decrement at all. So action potentials are non-decremental. So to summarize, what is going to trigger an action potential, cause an action potential to occur, is when the Hillock rises from -70 millivolts to -55 millivolts. That's what we call hitting threshold. Okay, that's what actually triggers an action potential and causes one to occur. That's not an action potential, that's what triggers it to happen. Okay, at -55 millivolts, all the voltage-gated sodium channels in the Hillock region will open up, sodium will rush in, and we'll get to +30. Now, an action potential, by definition, is this non-decremental electrical wave that travels down the axon into the axon terminals and into the axon terminal buttons. Non-decremental means as the electrical impulse moves, its potential, its membrane potential doesn't change. It doesn't dissipate, it doesn't decrement. The reason for that is because voltage-gated sodium channels line the entire length of the axon and keep the membrane potential stable as it moves throughout the axon. So last thing that we need to talk about before we talk about repolarizations and refractory periods, which will be very new, is how exocytosis happens. Okay, what about the whole purpose of an action potential is to spread into the axon terminals and into the buttons and cause exocytosis of neurotransmitters from the axon terminal buttons. It's to tell the vesicles within the buttons to go to the distal end of the buttons and dock and release their neurotransmitters into the interstitial fluid. So what about an action potential propagating into the button allows for this to happen? All right, here is an axon terminal, and here's a button. Okay, throughout the length of the axon terminal are voltage-gated sodium channels. Right, that's going to allow for the action potential to propagate throughout the axon terminal itself. Okay, so this wave of sodium ions is going to move into the axon terminal where it's still -70. It's going to make this region in the axon terminal more positive. Voltage-gated sodium channels are going to open up. Sodium is going to rush into the axon terminal, make this region of the axon terminal positive 30 millivolts. The sodium ions are going to get pulled into the next negative region, make that region positive enough so that the voltage-gated sodium channels open up. Sodium is going to rush in, and sodium is going to make this region positive 30 millivolts. Okay, so where are the sodium ions going to go to next? Inside of the button, it's still -70 millivolts. So the sodium ions, wave of positivity, is going to get pulled into the button. Inside of the button, instead of there being voltage-gated sodium channels, there are voltage-gated calcium channels. And they're triggered to open up just like voltage-gated sodium channels are, okay? So if this wave of positivity, these sodium ions, move into the button and make the button more positive, then the voltage-gated calcium channels embedded in the plasma membrane of the button will open up. Here's what we know about calcium. It's a positively charged ion that's high outside, low inside. So it has a chemical driving force to come into the cell, into the button in this example, specific portion of the cell. It also has a strong electrical driving force pulling it into the button, right? Because calcium, is a positive ion. The interior probably at this point is like -55 millivolts or so. Okay, so if you open up voltage-gated calcium channels, calcium is going to want to come in through both a chemical and an electrical driving force, and that's exactly what's going to happen. Calcium is going to rush into the button. So let me show you an image you've seen before. I didn't actually tell you the details of the previous image that we've looked at a million times, but I can actually use that image to show you what's going on here. So check it out. Here is the axon terminal. Embedded throughout the axon terminal are voltage-gated sodium channels. You know that as this region of the axon terminal becomes positive because of the influx of positively charged sodium ions, the voltage-gated sodium channels open up. Sodium rushes in, makes the axon terminal region positive 30 millivolts. Then the sodium ions get pulled into the button where it's still -70. That makes the button more positive, and look at that, the voltage-gated calcium channels open up in the membrane of the button. And calcium is a positively charged ion that's high outside, low inside. So it has a chemical driving force to come in. It also has an electrical driving force pulling it in. So if the voltage-gated calcium channels open up, as is depicted in the image, calcium will flood into the button. And the influx of calcium into the button is what triggers exocytosis of neurotransmitters. Okay, the influx of calcium into the button is actually what triggers the vesicles to go to the distal end of the button, dock, and then release their neurotransmitters into the interstitial fluid. More specifically, the interstitial fluid that exists in the synaptic cleft, the space that exists between the axon terminal button and whatever cell that it hooks up with. In this case, we can say another neuron. But as you all probably know or remember, neurons don't always hook up with other neurons. This could be another cell. It would still be a synapse. Right? It would just be an axon terminal button, for example, meeting a skeletal muscle fiber. Okay, that's still a synapse. Where the axon terminal button of a neuron, the presynaptic neuron, meets another cell. If the other cell is not a neuron, it doesn't matter, right? It's still a synapse. But for the sake of making things easy, let's pretend that the other cell that the axon terminal button is forming a synapse with is another neuron. So let's imagine this. The action potential is propagating down the axon of neuron number 2 here. Okay, and that's why I actually like to number these and not call them postsynaptic neurons, because the postsynaptic neuron is now going to become the presynaptic neuron, because I'm going to show you it hooking up with another neuron. The terminology is technically accurate in looking at this. Neuron number 2 is the postsynaptic neuron, but when you start talking about the neuron that the neuron number 2, the postsynaptic neuron, hooks up with, which we'll say is over here, now the postsynaptic neuron becomes the presynaptic neuron, so I just prefer to number them. So this is neuron number 1, this is neuron number 2, and over here we have neuron number 3. I've shown you what I'm showing you is its cell body, its dendrites, and here we'll say is its axon. Okay. So neuron number 1 generated an action potential. It actually generated around 100 action potentials per second. And neuron number 1 then released a lot of neurotransmitters onto neuron number 2 over the course of a second. That allowed enough sodium ions to come in to neuron number 2 so that enough sodium ions actually got into the hillock of neuron number 2 to make the hillock rise to threshold. 15 millivolts more positive. Then the voltage-gated sodium channels in the hillock of neuron number 2 opened up. Sodium rushed in, made the hillock positive 30 millivolts. And what this really means is now we've generated an action potential. What's going to happen is, since we got neuron number 2 to get the hillock region within neuron number 2 to rise by 15 millivolts, negative 70 to negative 55, neuron number 2 is going to generate an action potential, a non-decremental electrical wave that's going to travel down its axon into its axon terminals and into its axon terminal buttons. The reason it's non-decremental, again, the voltage doesn't change as it propagates. It's because voltage-gated sodium channels line the length of neuron number 2. Neuron number 2's axon, I mean. Okay, so the action potential then propagates into neuron number 2's axon terminal buttons. And instead of voltage-gated sodium channels existing in the buttons, there are voltage-gated calcium channels, and they open up, which allows calcium to flow into the buttons of neuron number 2. That's the whole purpose of the action potential. The purpose of the action potential is to propagate into the buttons of that specific neuron and cause or allow for calcium to actually flow into the buttons of that neuron, so that then the influx of calcium can tell the vesicles within the buttons of that neuron to go to the distal end of the button and dock and release their neurotransmitters through exocytosis. So you can say, the purpose of the action potential is to cause exocytosis of neurotransmitters, which is true, but how is it actually doing that, right? Really, the purpose of the action potential is to flow into the buttons and open up voltage-gated calcium channels in the buttons so that calcium can come in, and then actually the influx of calcium is what triggers exocytosis of the neurotransmitter. So it's a little bit more nuanced than just simply saying action potentials cause exocytosis. It's more detailed than that. All right, so these neurotransmitters through exocytosis are now leaving the axon terminal buttons of the neuron number 2 that just had an action potential travel down. Now, what type of neurotransmitters are these? That's highly specific to the different regions of the nervous system, and even in that specific region of the nervous system, which type of neuron you're talking about. So all I'm going to say is that neuron number 2 is releasing some type of excitatory neurotransmitter. Maybe it's glutamate, maybe it's acetylcholine. It all depends on the neuron and the part of the nervous system that you're within. So it's impossible to talk about this, really generically and then, give you a specific neurotransmitter. I'm just going to say it's an excitatory neurotransmitter. What's this excitatory neurotransmitter going to do? Well, I just told you, let me erase this real quick. The neuron number 2 hooks up with neuron number 3. Okay. Here is neuron number 3's dendrites. Okay. So neuron number 2 synapses with the dendrites of neuron number 3. Neuron number 2's axon terminal buttons synapse with the dendrites of neuron number 3. And neuron number 2 is releasing excitatory neurotransmitters into the synaptic cleft. So you can imagine on the dendrites of neuron number 3, attached to the dendrites or embedded in the plasma membrane of the dendrites of neuron number 3, there are going to be ligand-gated channels that bind this specific neurotransmitter. And that neurotransmitter is going to bind to those ligand-gated channels on the dendrites of neuron number 3, and it's going to cause them to open up. And if it's an excitatory neurotransmitter, I can tell you the ligand-gated channels, again, are probably going to be these non-specific cation channels, which is going to allow for the influx of sodium ions into the dendrites of neuron number 3. Within the dendrites, you're going to get a small depolarization. Now, if neuron number 2 only generates one action potential, what I can tell you is, and you should know this at this point, that's not going to be nearly enough sodium to actually flow all the way into the region of the hillock of neuron number 3 and make the hillock get to threshold. Potentials that come from the dendritic regions are decremental, right? They dissipate as they move away from the site of origin because voltage-gated sodium channels don't exist until you get to the hillock. So if neuron number 2 only fires one time, you can be quite certain neuron number 3 is not getting to threshold. But if neuron number 2 can fire, let's say, 100 times over the course of a second, it will release enough excitatory neurotransmitters to bind to enough ligand-gated channels on the dendrites of neuron number 3 to allow enough sodium in, so that enough sodium will actually get in to the hillock region of neuron number 3 to make the hillock region 15 millivolts more positive, and threshold will be hit, and an action potential will then occur. And now, a non-decremental wave of electricity positivity, called an action potential, is going to propagate down the length of the axon of neuron number 3 and into the axon terminals and axon terminal buttons of neuron number 3. And now neuron number 3, will release through exocytosis its neurotransmitters, because voltage-gated calcium channels within neuron number 3's axon terminal buttons will open up and trigger exocytosis. And this is the way that neurons communicate with each other. Another way of saying this is the way that neurons pass action potentials to each other. And that is the end of this review portion of kind of neuronal communication, synaptic transmission, and action potentials. What we will talk about from this point on is all going to be new material, because what we need to talk about next is how the neuron repolarizes and these things called refractory periods. They're incredibly important to understand different theories related to all different cells within the body, all sorts of different cells. At the beginning, I said I was going to combine all of it together, but I'm just going to use this video and the previous video as both review videos, and starting with the next video lecture will be all new content.